Hi, welcome to our second day in lesson 2-3 about polynomial functions and their graphs. Today we're going to look at a couple of key elements of graphs, and we're going to focus on how to graph a polynomial by hand. So should be exciting for all of us. As you look at the set of 4 graphs that are here, what we're asking you to do in this activity is look at how many turning points they have. That is, where do they make a turn from one direction to another. And as you look at the first one, the line f of x equals negative 2x plus 4, I'm not seeing any turning points there, so I think we can safely say that that's a 0. In the quadratic equation, negative 2x squared plus 4, we have one turning point right here. And as you look at the cubic polynomial here, we turn once, we turn twice. 2 turning points here, and I'll bet you that you're starting to see a pattern. How many do you suppose we're going to find in this function that would have, let's see, 2 powers of x, 3 powers, 4 powers of x? Based on what we've seen previously, I'm thinking 3 turning points. Let's see if we can find those. Here's one for sure. Here's a direction change, and here's a third. So I'm thinking, yeah, we've got those 3 turning points in this one as well. So based on what you see, I'm wondering if you could make a conjecture, which is really an educated guess, about how the degree of a polynomial and its number of turning points are related. What do you think? Well, the rule says, and you can confirm that on pages 309 to 311, that the number of turning points will be at most 1 less than the degree of the polynomial. The number of turning points is at most, it means it can't be any more than 1 less than the degree. And we saw that borne out in these functions very clearly. All right. The next thing, really the last thing that we have to do in this section, is think about graphing a polynomial. So we're going to pull it all together here. You use the leading coefficient test to determine end behavior. And you'll remember that there are 4 cases that we can discuss. You find x-intercepts, folks, by setting f of x, or setting the function equal to 0, and solving for x. That can be done with the quadratic formula, with factoring, etc. Check for multiplicity, that is, are there roots that show up more than once? More than once, that's pretty sloppy. You find the y-intercept by setting x equal to 0 and solving for y. Or if the polynomial happens to be multiplied out, then the constant term is its y-intercept. Use symmetry if possible, folks. All even exponents mean the graph reflects over the y-axis. All odd exponents and no constant term mean that the graph rotates 180 degrees about the origin. So those symmetry rules that we learned a long time ago will be helpful here. Use the degree, and this is our final clue. Use the degree to determine the number of turning points. And you might have to locate turning points by looking at a table. Unfortunately, without using calculus, there's no surefire way to determine where those turning points are. So locating them means looking sometimes at a table. Let's see how that plays out here. our polynomial is x to the 4th power minus 2x squared plus 1. So we should be able to come up with 4 roots here. Our graph, well, its end behavior should be, you tell me, we're an even degree positive leading coefficient. I'm hoping we're thinking up, up. X-intercepts, we're going to find those by setting the function equal to 0 and solving for x. So we want to solve the equation 0 equals x to the 4th power minus 2x squared plus 1. And even though this is a 4th power, we still should be able to apply perhaps some of the factoring patterns here. Boy, that is just a lousy looking 4. X to the 4th power minus 2x squared plus 1. That is a perfect square, as is that. And I'm looking at this thing thinking the coefficient here is twice as much as here. I believe, folks, that we can apply one of the factoring patterns here. This is a x squared. It's going to be minus 1 times x squared minus 1. Again, I looked here, perfect square, perfect square. The coefficient on the middle term is exactly twice the square root of this. So it factors in that this is the, it's a perfect square trinomial. Each of these guys is a difference of squares, and that tells us something, that each of them will factor down further to x plus 1, x minus 1. That's the first parenthesis. The second factors the same way, x plus 1, x minus 1. And that means that our x's are going to be positive and negative 1 with a multiplicity of 2 for each of those. So we're going to, since we have a multiplicity of 2, we're going to bounce at negative 1 and bounce at positive 1. Our y-intercept is 1, and I'm getting that because it's the constant term here. Whoops. Our roots are at negative 1 and positive 1, and both of those are bouncers. We know that since we have multiplicity of 2, that we are going to have bounce spots here, as we were saying. And with up, up, and behavior, our graph is going to fit in here something to the tune of this. And I am pretty sure about the symmetry. Since our graph is somewhat, or since our rule is somewhat symmetric, we should see a symmetric graph. The bounce points, it can never go below those, and it will not. It has a relative maximum here. The x-intercepts then we found, the y-intercept we got from the rule. Symmetry, we use that to graph, and we know that in a 4th degree polynomial we should have at most 3 turning points, so we should just check that. There's 1, there's 2, there's 3. I think we did a pretty good job at nailing that graph, folks, but the best way to tell, of course, is to check with that calculator. So let's grab the calculator, set up a new graph page, and our function was x raised to the 4th power minus 2x squared plus 1. And our standard window should be correct, at least if we graphed it right. So let's take a quick look. Hey, not bad for rookies. What do you think? I think we graphed that thing, folks. So our work in class tomorrow will revolve around graphing polynomial equations by hand. So I hope you enjoyed the video, and we will see you in class the next period.